Hi, my name is Kenny Jones, and I'll be presenting SHRED, 3D Shape Region Decomposition with Learned Local Operations. This is joint work with Aalia Habib and Daniel Ritchie. SHRED is a method for 3D shape segmentation. This is a fundamental problem within computer graphics and vision. As a general framing of the problem, typically we assume that we get a 3D shape as input, and as output, we want to partition the input shape into disjoint sets according to some criteria that is application dependent. There are many applications across visual computing disciplines that require methods capable of producing high-quality segmentations, such as skeleton extraction, guiding semantic labeling, and allowing autonomous agents to interact with objects, to name a few examples. In this work, we are interested in producing segmentations that approximate fine-grained part instances. Recently, many learning methods have been explored for this setting, and they produce impressive results for coarse part decompositions when there is abundant training data, but they often struggle when fine-grained parts are desired or when labeled data is limited. So while they might succeed on categories of objects that have many available annotations, such as lamps or chairs, they won't do as well on less typical object categories, such as earphones or faucets, where annotations can be harder to acquire. SHRED aims to address this problem by learning how to segment shapes in a way that generalizes across domains. If we learn how to perform segmentation in a domain-agnostic manner, then we can train our model on categories of shapes that have abundant annotated data, and then hopefully our method will have learned decomposition policies that can be directly applied to shapes from new categories that lack annotations without any additional training. The question remains how to learn a policy that generalizes across domains. The intuition we employ here is that while reasoning over global part segmentation is highly domain-specific, the local part segmentation tasks can be very similar across different domains. To this end, SHRED learns 3 shape decomposition operations that are only allowed to reason locally: splitting a region into subregions, fixing the boundaries between neighboring regions, and merging neighboring regions together. We find that SHRED's locally learned operators, when trained on data-abundant in-domain categories of shapes, learn decomposition policies that generalize much better than comparison methods when applied to shapes from out-of-domain categories not seen during training. Now let's look at how SHRED's framing differs from what's been done before. We can roughly break up approaches for 3D shape segmentation into 4 categories. This first group of approaches includes methods that aim to segment a shape into meaningful regions according to geometric properties. This bucket would include most of the traditional computer graphics approaches that aren't data-driven, but rather rely on heuristic properties of input shapes, often surface meshes, in order to decide on a good shape partitioning. The advantage of these methods is that they don't overfit to a single category of shapes, as there is typically no learning. But the downside is that it's a very difficult problem to find a heuristic that works over a large collection of input shapes, and these approaches typically can't leverage the information from annotated examples that do exist in large datasets. An alternative strategy is to employ a learning-based method that attempts to represent a 3D shape as a collection of simple primitives, which can then be used to segment the input shape. The advantage of these methods is that as they can train in an unsupervised fashion, they don't require part annotated training data. The downside is that these approaches use global reconstruction losses, which encourage primitives to capture the core structure of input shapes, but often ignore fine-grained parts. However, most learning-based shape decomposition methods operate within a supervised learning paradigm by consuming a training dataset that contains annotated regions. The standard approach in this supervised paradigm is to learn how to globally decompose a shape, often in a category-specific fashion. As previously mentioned, methods in this group achieve remarkable success on coarse segmentation tasks for in-domain categories with abundant label data, but they often struggle when any of these conditions are not met. Most similar to SHRED, there have also been some recent approaches that have developed learning-based solutions that incorporate local reasoning. In learning fine-grained segmentation of 3D shapes without part labels, or WOPL for short, a prior net performs a split-like operation in a local fashion that is followed by a global merge predicted by a merge net. In learning to group, a bottom-up framework for 3D part discovery in unseen categories, or L2G for short, a policy module and a verification module are trained in a reinforcement learning paradigm to decide when subparts should be grouped together in a merge-like operation. We experimentally compare SHRED against these approaches, and we find that SHRED's collection of learned local operations improves the quality of its region decompositions over these alternatives. Now I'll describe our method for 3D shape segmentation. SHRED takes a 3D shape as input and outputs a fine-grained region decomposition. We represent 3D shapes as high-resolution point clouds sampled from a surface mesh, as shown in the left. SHRED creates a segmentation by assigning a region to each input point, as shown in the right, where points in the same region share the same color. SHRED produces segmentations by running the input shape through 4 stages in a sequential fashion. As SHRED's learned operations all reason locally, the first step is to create a naive initial decomposition of the input shape. While there are many approaches that could be used here, we found that a simple farthest point sampling clustering procedure proved both fast and effective. Unless otherwise specified, we use 64 centroids in the FPS stage. The split operation breaks regions into subregions. It consumes the region's output from the FPS stage, where each region might be an undersegmentation with respect to the ground truth parts. To remove this undersegmentation, the split operation uses a split network that we model with a PointNet++. The split network consumes points from a single region as input, as shown in gray on the left, and then makes an instant segmentation prediction for each input point, shown with the different colors on the right. In this example, the split network identifies that the input point cloud should be divided into 2 subregions, one for the vertical pole in red and one for the horizontal plane in green. The split operation runs a split network on every input region and then propagates these predictions back to the global shape view in order to produce an over-segmented output decomposition. The fix operation is responsible for improving the boundaries between regions. It consumes the region decomposition output by the split operation. This decomposition is often fine-grained, but it might contain errors on region boundaries, as a split network receives no information about the shape outside of each region. To accomplish this goal, the fix operation uses a fixed network that we model with a PointNet++. The fixed network operates over individual regions, shown in color on the left, but also receives nearby points from outside the region as input, shown in gray on the left. The fixed network is tasked with making a binary prediction for every input point of whether or not that point belongs to the region, which we represent with the colored versus gray points on the right. For instance, in the top row, the spurious blue input points on the vertical bar are predicted to be outside the region, as they get colored gray, while the gray input points on the horizontal bar are predicted to be inside the region, as they get colored blue. The fix operation once again applies a fixed network to every input region, and then propagates each local prediction back to the global shape view in order to produce a shape decomposition with better aligned boundaries. The merge operation decides when neighboring regions should be combined. It consumes the output of the fix module, so typically the input decomposition contains little undersegmentation but uses many more regions than necessary. The merge operation uses a merge network modeled with a PointNet++. The merge network operates on points sourced from 2 neighboring regions, represented with different colors, along with points from a local neighborhood that don't belong to either region, represented with gray. This network makes a single binary prediction of whether or not the 2 regions should be merged together. We convert this prediction into a probability and then complete the merge if the prediction is above a merge threshold hyperparameter. 2 regions should be merged if the ground truth region they share the most overlap with is the same. For instance, the orange and dark blue regions both overlap with the horizontal bar part, so they should be merged, while the light blue region overlaps with the vertical bar part, so it shouldn't be merged with the orange region. The merge operation runs the merge network iteratively over all pairs of neighboring regions until all remaining pairs have been considered. This final set of regions is then considered as the output of the SHRED method as shown on the right in the top row. To understand the effect of these locally learned operators, we evaluate SHRED's ability to produce high-quality region decompositions of 3D shapes. We use shapes from the PartNet dataset with the finest grained part annotations as the target segmentations. We trained Shred on shapes from 3 in-domain categories: chairs, lamps, and storage furniture. We hold out 7 out-domain categories of shapes that we use to evaluate Shred's generalization capabilities. Shred is trained on all 3 in-domain categories at once, with 2,000 shapes from each in-domain category to form a training set of 6,000 labeled shapes. The networks within the split, fix, and merge operations are all trained independently and use the fine-grained part labels along with synthetic perturbations to construct input-output paired data for each network. We perform early stopping using a validation set of 600 in-domain shapes and evaluate on a held-out test set where each in-domain and out-domain category contributes 200 shapes. However, we still need to figure out how to evaluate 3D shape segmentation success. For instance, consider this input shape, along with a ground truth human-provided fine-grained part annotation, R star. Now consider these 2 different segmentations of the input shape, R1 and R2. Which should we prefer? In R1, some regions, like the top of the lamp, are undersegmented with respect to R star. However, while R2 has very little undersegmentation, it also uses many more segments than are present in R star. With this in mind, given a ground truth annotation R star, we desire a region decomposition R that satisfies 2 properties. First, the number of regions in R should not exceed the number of regions in R star. Otherwise, there will be oversegmentation. Second, each region of R should not be a subset of some region in R star. Otherwise, there will be undersegmentation. Notice that these 2 properties work against one another and are in fact only satisfied when R is exactly equal to R star. So we design metrics that measure violations of these 2 properties. We can easily measure violations of the first property by just counting the number of regions in the output segmentation. We call this measure decomposition granularity. To measure violations of the second property, we use a metric called region purity. This metric takes values from 0 to 1 and is equal to 1 only when all predicted regions are subsets of ground truth regions, but its values are not sensitive to the granularity of the predicted decomposition. We can now consider the trade-off that different methods make in this decision space by plotting granularity on the x-axis and purity on the y-axis. In this graph, we want to be closest to the top left corner, as this would make the best trade-off between region purity and decomposition granularity. We show results for different 3D shape segmentation methods, with in-domain results on the left plot and out-domain results on the right plot. We compare Shred in blue against a suite of comparison methods. Approximate convex decomposition, or ACD, and farthest point sampling, or FPS, are non-learning based approaches. PartNet instant segmentation, or PNSeg, is a learned approach that operates globally, and LTG and WOPL are the aforementioned related works that also use local learning. From this view of the results, it appears Shred is doing well, but it's hard to directly compare methods as they all provide results at different points in the solution space. Fortunately, Shred exposes a tunable hyperparameter, the merge threshold, that can modify the granularity of the output decomposition at inference time. We'd leverage this property to plot Shred decomposition results as a frontier curve. This allows us to evaluate Shred fairly against all of the other methods, as we can compare region purities at any level of granularity. So not only does Shred have a built-in mechanism that allows the granularity to be varied at inference time, but in all cases, we find that the Shred frontier dominates the other methods, indicating it finds a strictly better trade-off between granularity and quality. In these results, we show what effect varying the merge threshold hyperparameter has on the output decompositions. We show segmentations produced by Shred with 3 merge threshold settings. From left to right, these are 20%, 50%, which is the default setting, and 80%. When the merge threshold is set below 50%, more regions will be merged together, and as the merge threshold is increased, the decomposition will be more fine-grained. We also show that the decompositions produced by Shred can be treated as fine-grained part instant segmentations. Here we depict some qualitative outputs on in-domain test set shapes, comparing segmentations produced by baseline methods in the left 3 columns against the segmentations produced by Shred in the 4th column, where the ground truth annotation is shown in the rightmost column. As evidenced, Shred is able to provide high-quality segmentations that work well across multiple categories. Here is a similar qualitative evaluation setup where we show predicted segmentations made by different methods over out-domain shapes. Even though Shred has never seen shapes from these categories during training, it is still able to segment the inputs quite well. For instance, it is the only method that is able to differentiate the table drawer from the table top in this example. We evaluate each method's ability to perform fine-grained part instance segmentation with an average IOU metric that measures agreement between a predicted and ground truth segmentation. We find that Shred significantly outperforms comparison approaches for both in-domain and out-domain averages. Additionally, we examine how Shred can be used to improve fine-grained semantic segmentation performance when access to labeled data is limited. We combine Shred with a recent approach, NGSP, that learned how to semantically label part regions. We compare predictions made by Shred with NGSP against a baseline version that does not label shape regions, and find that Shred's region decompositions better match ground truth annotations, as they regularize the predicted semantic segmentations. Quantitatively, we find that when using 10 or 40 labeled exemplars, Shred regions lead to semantic segmentations with higher mean IOU compared with alternative region decomposition approaches, or not using regions at all. Here we show results from our ablation experiments to answer the question of how training data affects the performance of Shred. First, note the average IOU performance of Shred and the best performing baseline method for both in-domain and out-domain categories. We retrained versions of Shred on just one category of shape. These experiments are the chair-only, lamp-only, and storage-only bars. As can be seen, training on a single category significantly hurts Shred's performance. However, if we retrain Shred with the same 3 in-domain categories, but use only 10% of the data per category, the performance remains strong. In fact, this version achieves better average IOU than the best baseline method or any single category trained version. To conclude, there are many exciting avenues of future work within this space. While Shred has demonstrated an impressive capacity to generalize to out-of-distribution instances, all of the shapes we've experimented with come from the same meta-distribution of manufactured objects. It would be interesting to investigate how Shred generalizes to more diverse domains, including those that share locally similar properties, such as partial shape scans or 3D scenes, or even to domains that share hardly any similarities, such as organic bodies. Along another direction, while Shred's merge threshold allows some exploration over a range of decomposition granularities, the segmentation that Shred produces are always flat. Developing a procedure to convert this series of flat decompositions into a shared, hierarchical segmentation may prove useful for various downstream applications. Finally, while we find that Shred's sequential application of the split, fix, and merge operations results in region decompositions that outperform previous approaches, it's unlikely that the sequence is optimal for every shape instance. Shred's performance could likely be improved by wrapping the operators of Shred with a more advanced scheduler that can tailor which operation should be applied where in what order for a particular input shape. We have a project page for Shred with links to release code, which can be found at the listed address. Thanks for listening, and please feel free to reach out for additional information, questions, or clarifications.